Sunita ma'am, we can start the session at 10 a.m., right? A few more participants have to join, ma'am. Yes, ma'am?
Yes.
Okay.
Let them join.
Okay, ma'am. Okay, ma'am. Thank you, ma'am.
Welcome, Sunita ma'am. Sunita ma'am.
Yes, I am here. Can you hear me?
Hello, ma'am. Am I audible?
Yes, can you hear me?
Yeah.
You are audible. Can you hear me?
Yes, ma'am. Yes, ma'am. I can hear you.
Yes. No. Can you see me?
Welcome to our session.
Okay, fine.
Ma'am, happy to see you after a long time, ma'am.
Even I. When you were a BOS member, you used to come at least once in a year.
But also conducting online only, right? All the BOS meeting we conducting nowadays online only.
Yes, ma'am. Yes, ma'am. Swarna miss, should we start? It's already 9:55, I think.
Yeah, 9:55. 39, 40 have joined. I think we can start.
Sunda ma'am, shall we start, ma'am?
Yes.
Ma'am, I think your voice is breaking, ma'am.
How now?
Okay, but still, I think. Ma'am, could you say something, ma'am, so that we can?
It's a great honor to be a part of our webinar series. Adore Vimala for inviting me.
Yeah, your voice is breaking, ma'am. A little bit problem is there.
Okay.
You just switch off your video and see, ma'am, whether.
So now can you hear me properly?
Yes. Now we can hear. Yeah.
Okay.
Okay, so we shall start. Arya, we can start, I think. Yeah.
Okay, a great morning to one and all. We all know that today is the third day of our webinar series. Today we are so glad to have Professor M.S. Sunita, the Professor of NIT Calicut, to handle the session on Introduction to Fuzzy Logics. So we can start the program by a silent prayer. Thank you. Now I welcome Ms. Jolly Agustin, Assistant Professor of Vimala College, Thrissur, for the welcome speech.
Respected Principal, Dr. Sister Veena Jose, Professor Dr. Sunita M.S., our DBT Staff Scheme Coordinator, Dr. Sister Sylvie Matthew, our Head of the Department, Srimati K.L. Sarna, Program Coordinator, Dr. Anjali Kishore, my colleagues, my dear students, and all the participants. Today is the third day of our webinar series on pure and applied mathematics. My hearty welcome to all for today's program. I am very glad to introduce to you today's speaker, Dr. Sunitha MS. Dr. Sunitha is a professor of Department of Mathematics, National Institute of Technology, Calicut. She took her PhD from Cochin University of Science and Technology. Her areas of expertise are fuzzy graphs and discrete mathematics. She mentored 11 PhD scholars, including our program coordinator, Dr. Anjali Kishore. She published 62 papers in various national and international reputed journals and is the author of 14 books or chapters. She is very passionate about research and she is very close to us as she is the guide, she was the guide of our Dr. Anjali. I extend a hearty welcome to our dear Dr. Sunitha. And once again, I welcome each and every one of you. Thank you.
Thank you for your kind words. I'm very new for the webinar series and happy that this is my first webinar starting today. So very thankful to the of the Villa College. I thank all the staff and students, participants of the webinar series. Thank you once again for inviting me to our series. Okay.
Thank you, ma'am. Thank you. You can start.
Can I start now?
Yes, ma'am. Yes, ma'am.
Yeah, you can start.
Now I have shown you the first is first talk. Tell me whether the screen is with.
It is loading, ma'am. Yeah, now it is seen, ma'am. Yes, ma'am. But still, your voice is breaking, ma'am. I don't know if it is a problem with me. Swarna,
Okay, wait, let's see.
Okay, okay, ma'am. Okay, ma'am.
Introduction to fuzzy and restart the topic fuzzy sets. The definition of fuzzy set, how we can continuously put logic or is called the fuzzy logic. Okay. So all of you know that the logic or the logic, which already know. The uncertainty, which is characterized by the logic. We have the slide, next slide here I have shown you. Please, this new slide is visible to you.
Yes, ma'am. The slide is visible, but your voice is breaking.
Okay. Breaking up.
Yeah. Yeah. Now it is clear.
Clear?
Yeah, now it is clear.
Okay. So, okay. Uncertainty, we are talking about uncertainty, but what type of uncertainty? Sir, mathematically, and the concept of uncertainty is divided into two classification. That is, that impression is divided into two. First one is what is called vagueness, and the second one is called ambiguity. But for a uncertainty or imprecision or vagueness or ambiguity means the same. But you can see the dictionary word meaning of all these concepts. Vagueness should distinguish from the concept of ambiguity. Though the layman, all these concepts are same. But mathematically, we distinguish the uncertainty into two classes, vagueness and ambiguity. The concept of vagueness, how will you express the concept of ambiguity will you express in mathematical terms? So that is what now I am going to explain to you. Now that the vagueness means a difficulty of making sharp distinction. I shall the concept of what is difficulty of sharp distinction. Example, if you take a suppose there are 50 students, then in IQ varies the student to student. Who is the most intelligent student, or the second intelligent student, or the third intelligent student? So how to identify intelligent student? So who is the full student class? How will you identify the beauty of a student in the class? That also is a question. So vagueness means distinction. Okay, the concept of beautiful or the concept of intelligence, you cannot make a sharp boundary there. Classification of yes, this student is beautiful as that, or both students are beautiful or the same thing. You can make a distinction. It is very difficult to make boundaries here. Such type of uncertainty is what is called vagueness. Difficulty making sharp distinction. Okay, and what's the concept of certainty, that is vagueness, is what is more the theory of fuzzy. So fuzzy sets is depending on the vagueness, that difficulty making sharp distinctions. Was developed by Locke in 1965. Okay? Similarly, the second classification of ambiguity, mathematically, it is between of two or more alternatives. By two or more what? Let's tell you again one example here. Suppose maybe first we don't know. We are getting well or something like that. And want to find the particular vessel belongs to. So certainty, is what is called the ambiguity. That type of uncertainty is what is called ambiguity. Example identify ambiguity. The equations. Suppose there are some equations P1, P2, P4
Hello,
are
ma'am.
approaching dot. Yes.
Hello,
Yes,
ma'am.
yes.
May I interrupt in between? Ma'am, the slides
Yes.
are also a bit blurred and your voice is not so clear, ma'am.
And wait for 2 minutes.
Okay,
Okay.
okay, ma'am. Okay, ma'am. Sure, ma'am. Okay, ma'am. Thank you. I request all the participants to please wait patiently so that the resource person can rectify her glitches. Thank you.
Now, Dr. Anjali, can you hear me now?
Yes, ma'am. Yes, ma'am. Now it is clear, ma'am.
Okay.
Sorry to disturb you, ma'am, in between.
No, that's okay. This happens, no? This happens. Now I have shown you
Yes,
the
ma'am.
same
Yes.
slide. I have shown you the same
Yes, ma'am.
slide. Please tell me when this is visible.
Okay, ma'am. Okay, ma'am. Sure.
Is the slide visible now?
No, ma'am. I think you have not started presenting it, ma'am.
Okay. Okay, fine. Let me see.
Okay. Okay, ma'am.
Dr. Anjali, how is it now?
Yes, ma'am. It is seen that it is presenting, but
Okay,
the
wait.
slides are
Yeah,
not.
wait.
Yeah.
It will
Okay.
come.
Yeah. Okay. Okay. Okay, ma'am. Okay.
Screen is still not visible?
It's not visible to me, ma'am. Have you started sharing the slides, ma'am?
Yes, I have shown you the slide here.
Yeah, but
But I
we
think
can't see it, ma'am. It's not visible.
Is it?
Now we can see your phone, but not your slides, ma'am. Ma'am has left. Yeah.
No, ma'am is still there. She's doing it, I think. Yeah.
Yeah. Participants, please bear with us. I think it is due to the bad weather in Kerala.
Yeah, it has been raining heavily from since morning, right?
Yeah.
Yes, ma'am. Now the slides are visible. Yes, ma'am. Yes, ma'am. Yes, ma'am. Now it is very clear. Sunita, ma'am. Sunita, ma'am, I think your audio is muted, ma'am. Ma'am, now the slides are very clear, ma'am. But your audio is not coming. Yes.
Dr. Anjali, can you hear me now?
Yes, ma'am. Yes, ma'am.
Slide also?
Slide it is coming that it is presenting. Yeah, now we
Okay.
can see, ma'am. Yeah, ma'am. Thank you.
Okay.
Thank you, ma'am.
So there are 5 patients, P1, P2, P3, P4 and P5. All are approaching a doctor with a common symptom of fever. Now the doctor will be in a dilemma whether the fever is simply a fever or it is the symptom of any other disease, say DI. Then doctor will be prescribing some lab tests to identify the actual disease. But till that time, till the identification, the doctor is in an ambiguity, right? But once the diagnosis is over and suppose the disease of the patient PI is identified, then there is no ambiguity at all. That patient will be now treated for that particular disease. So this type of uncertainty, or what is called ambiguity, which disappears after some time, is what is called ambiguity. And this second type of uncertainty, that is ambiguity, is modeled through the concept of what is called fuzzy measures by Sugino, etc. So as I told you, there are basically two types of uncertainty. The first one is vagueness, which is modeled through the theory of fuzzy sets, and the second one, ambiguity, which is modeled through the theory of fuzzy measures. Today, we will be concentrating only on the first type of uncertainty, which is vagueness, and that is the basic of the theory of fuzzy sets developed by L.A. Sade in 1965. Now, I have shown you the slide of vagueness. Please tell me when this is visible.
Yes, ma'am, it is visible, ma'am.
Okay, so let us study what is vagueness, or what is the theory of fuzzy sets. Now, the first question arises, why we require fuzzy sets? Because we already have the classical set theory, and we already developed so many mathematical tools using classical set theory or the two-valued logic. Now, what is the need for fuzzy sets? Are crisp sets sufficient or not? But in crisp sets, what is happening? You know, there are only two alternatives, that is belongs to or not belongs to. Means what? Given any set A, you can say whether a particular element belongs to it or whether it does not belong to it. For example, in a class, again I take a class of say first year degree students. Then suppose one exam was conducted and they have got marks for that particular exam. Then the teacher wants to classify the group of students in that class based on their marks. Suppose the teacher classifies the first group as all those students who got mark 90 and above out of 100. Then the second classification, all those students who got marks between 80 to 89. It continues like that. Now you can tell clearly whether a particular student belongs to which class or the particular student does not belong to a particular class. So the definition is very clear. Okay, the concept of set is very clear. You can tell whether an element belongs to it or does not belong to it. And when a particular element belongs to that particular set, then we call its membership value as 1. And if that particular element does not belong to the set, we say its value is 0 or the membership value is 0. And here in crisp set, so I will call the classical sets as crisp set now. What is happening is partial membership is not allowed. Now, what do you mean by partial membership? What do you mean by partial membership? That is, there may be statements which are completely true, 100% true, and there may be statements which are 100% false. But nowadays, you know, there are statements which are partially true or which are partially false also. But in crisp set theory or in classical set theory, we can incorporate only those statements which are completely true or which are completely false. If the statement is completely true, we assign the membership value, say 1, to that statement. And if the statement is completely false, we'll assign the truth value, say 0, to that particular statement. But nowadays we know there are statements which are partially true or which are partially false. Then which truth value we should assign to these partially true or partially false statements? So this particular problem is not taken into care by the classical set theory or what is called crisp set theory. So to overcome this situation, L.A. Sade in 1965 has developed the theory of fuzzy sets which allows the partial membership as well. So there are statements in between the complete true and complete false statements which will have the truth values, say between 0 and 1. Now here comes a photo or a picture of why we require fuzzy sets. Now please tell me when this slide is visible to you, the new slide.
Yes, ma'am.
Yes,
It is
ma'am.
visible,
Yes,
ma'am.
ma'am. It's with
So what it says, what is the reason for developing fuzzy sets? What is happening here? You can see there is a man standing in the middle and one stone is coming towards him. And what the left person or the precision says, what is precision? What he says is a 1,500 kilogram mass is approaching your head at 45.3 meters per second. But what the second person on the right says, what is that? Look out. So which one is more effective? Please tell me, students, please respond, which one is more effective in this type of situations, whether precision or imprecision? It is very clear that in these type of situation, no mathematics and no science will help you. You have to act immediately, and the second person here is saying just look out, and he has to move away from that particular situation to avoid danger. So that is, in our social life we come across many situations which are vague in nature, and or uncertain in nature. So how to take care of this vague data or how to take care of this uncertain data? We need a theory which is called fuzzy set theory. Okay, so in classical set theory we cannot take care of the vague data or the uncertain data. Of course, there is the probability theory we already know. In probability theory we come across some sort of uncertainty, right? The chance of happening of an event or chance of occurring of an event, that is incorporated in probability theory. But that is only a special case of what is called fuzzy measure theory that you can see later. So probability theory, what is developed, is now becomes a special branch or a special case of the ambiguity theory developed by Sugino, known as fuzzy measures. Okay, so now we are concentrating on fuzzy sets only, a generalized version of what is called probability theory. So you are now learning what is a generalization of a crisp set or what is generalization of probability theory. So let us see some more examples of situations where we have to come across vagueness. So I have shown you the slide of examples. Can you see it now?
Yes, ma'am. Yes, ma'am.
So as I told you, the first example, the collection of all new cars. Suppose in a locality, we count the collection of all new cars. But what is the concept of new? Whether it is brought on today or whether you can consider all the cars which are purchased during the last week or all the new cars which are purchased during the past 2 days, that depends on the particular situation that we are handling, or depend on the particular person who is handling the data or who is handling the problem. So you cannot clearly distinguish between a new car which is purchased today and which is purchased yesterday. Today purchase may be most new or yesterday's purchase may be not that new. But we cannot distinguish, there is no clear-cut boundaries between the concept of new car. Similarly, as I told you, the collection of all intelligent students, you cannot clearly distinguish between the intelligent students. Also, you cannot distinguish between the collection of beautiful girls. Okay, so in all these cases, the conventional classical approach fails. And you know already the crisp set theory or the classical set theory is developed on the basis of what is called characteristic function. Okay, and these fuzzy sets are nothing but generalization of characteristic functions. Now, what do you mean by generalization of characteristic functions? So let us see. Now, you already know the characteristic function. Suppose U is a universal set and you have only two truth values, say 0 and 1, and the characteristic function is nothing but denoted by chi of A from the universal set U to discrete interval 0, 1. Okay, and the definition is chi A of X equal to say 1 if X belongs to A and 0 if X does not belongs to A. Students, I have written something manually. Can you see it?
Yes,
Yes, ma'am. It is
Yes,
partly
ma'am.
visible, ma'am. I
It is
only
coming.
is visible.
It is coming now?
Yeah. Yes, ma'am. Yes, ma'am. Now it is come. Yes, ma'am. Thank you.
So what is chi of A? Characteristic function of the subset A of the universal set U. So I am denoting by U the universal set, and the characteristic is a function from the universal set to the discrete set 0, 1, defined by chi A of X equal to 1 if X belongs to A, and chi A of X equal to 0 if X does not belongs to A. Now, fuzzy sets are generalization of characteristic function. Means what? That is, the fuzzy set will be now a function from U to the closed interval 0, 1. So, instead of the discrete set 0, 1, if I take my range as the continuous of values in the interval closed interval 0, 1, then we denote that particular function by sigma A, and the function sigma A from U to the closed interval 0, 1 such that it takes the value 0 less than or equal to sigma A of X less than or equal to 1 for all X in the universal set U. Now, can you see the new text here, sigma A, the definition of sigma A which is written here?
Yes, ma'am. It is coming. Yes, ma'am. Yes, ma'am. Yes,
So,
ma'am.
okay, so sigma A is now a function from the universal set to the closed interval 0, 1, which takes the values in the interval 0 to 1 for all X in the universal set U. So now the sigma A becomes, the function sigma A becomes a generalization of the characteristic function chi of A, and the sigma A is what is called the membership function of the fuzzy set A. Now A becomes a fuzzy set which takes, whose members are taking the values in the interval 0, 1, including 0, including 1, and all the values in the interval 0, 1. So sigma A here stands for the membership function of the fuzzy set A. So that is how we define the fuzzy set as a generalization of the characteristic function. So let us see more examples in the next slide here. So I have given you the formal definition of the fuzzy subset. Please tell me when the new slide is visible.
Yes, ma'am. Definitions. It is visible, ma'am.
Okay, so the fuzzy subset. So usually we will not tell a fuzzy set. It is always represented or denoted as fuzzy subset only. A fuzzy subset of a set S is a mapping, say sigma, from S to the closed interval 0, 1. And the sigma is called the membership function. And the property of this membership function sigma is that the transition from the membership to non-membership is gradual rather than abrupt. What do you mean by that? It can continuously vary. The membership values can be varied continuously depending on each day, depending on each person. For example, the collection of new cars, a car which is new today, may be given the maximum membership value 1. But tomorrow, its newness is gone or decreased. So tomorrow, the membership value of the new car with respect to the car purchased today will not be 1, but it can be any number less than 1. That means today, those elements whose membership value are the whole 1 may not be the same next day. That is, it decreases gradually from membership to non-membership. So such types of transition occurs only in fuzzy sets, and thus the last sentence you can see, fuzzy sets are treated as continuously valued logic. Now what is the meaning of continuously valued logic? You know, in crisp set theory or classical set theory, there are only two truth values. Now, what do you mean by truth values? That is 0 or 1. Truth values means in crisp logic or classical logic, truth values means there are only two truth values, say 0 and 1. That is, the truth value of a statement, say P, is 1 if the statement P is true, and truth value of the same statement becomes 0 if the statement P is false. Can you see the writings here now, actually?
Yes, Miss. You can see.
Yes, ma'am. Yes.
So, this is what is happening in crisp logic. That is, only two truth values are there, 0 and 1 only. But in fuzzy sets, we can have the truth values which are taking the values within the interval, closed interval 0, 1. That is, all values between 0 and 1. You can assign the truth values to any statement in fuzzy logic. So that means the interval, closed interval, is a continuous interval having infinitely many points in that interval. So this fuzzy logic or fuzzy set can assume any value in the interval 0 to 1, which takes a continuum of values as the membership values, and that is why this fuzzy logic is treated as a continuously valued logic. I repeat, the classical logic or the crisp logic is called a two-valued logic. Only two truth values we can have, 0 or 1 only. But in fuzzy set, we can have any truth value in the closed interval 0, 1. And that is why, that truth values assume continuum of values, and that is why this fuzzy logic is treated as a continuously valued logic. Now here we have some mathematical example of a fuzzy set. So I have shown you the example of a fuzzy set. Please tell me when this is visible.
Yes, ma'am. It is visible, ma'am.
So I have taken an example, sigma, numbers close to 0. Now, how will you define this concept, numbers close to 0, using crisp set? How will you define? Numbers close to 0 means which number, whether integer or whether rational number or whether irrational number, or can you include negative numbers also? Nothing is given. Some vague statement as numbers close to 0 or the collection of numbers close to 0. So what is the meaning of close to 0? Whether close to 0 means whether the number should be integers or the number should be rational numbers which are close to 0. Nothing is specified here. Just the definition, numbers close to 0. So how will you represent this example? Now it is very difficult to express this example in the crisp logic. Suppose numbers close to 0 means, because it is not mentioned that integers close to 0, we cannot write the set as, say, we have the number 10 here, we have the number 10 here, and you know the integers close to 10. Which are the integers close to 10? 9 on the left, then 11 on the right, then 12 comes, then 8 comes, etc. Something you can write. On 10 also is very much close to 10. But you know, when it is not specified that integers, it is simply given that numbers close to 0. So how will you define this concept of numbers close to 0? For that, now make use of the concept of fuzzy set. So what I have taken here is, I have taken the number 10 as a middle point, and you know the number 10 is very much close to 10 than any other number. So what I do is, I shall give the maximum membership value, say 1 here. The maximum membership value along the y-axis is given for 10. That is, what I mean is, sigma of 10, the membership value of 10 is what? The membership, numbers close to 0. Numbers close to 0, so I shall take numbers which are close to 0. So the point is 0, so I should give the maximum membership value 1 to the number 0. So sigma of 0 should be 1. the maximum membership value to the number 0. Because 0 is very much close to 0. Now, what about the other numbers on either side of 0? You know, there are many other numbers which are on either side of 0, but they are at equal distance from 0. So, we think about a symmetrical curve about the point 0. So, a number say 0.5 to the right of 0, and similarly the number say minus 0.5 to the left of 0. They are close to 0 with respect to the distance, same distance from 0. So that means both these numbers, say 0.5 as well as minus 0.5, should be given the same membership value. For example, when you assign the membership value, sigma of 0.5 should be same as sigma of minus 0.5, but you cannot give the value 1 to both 0.5 and minus 0.5, because 1 is given to 0 and 0 is a number which is very much close to 0. And 0.5 is not that close to 0. Also minus 0.5 is also not that close to 0. So what happens is we have to assign some value which is less than 1 to these two numbers. Suppose I am assigning say as 0.95. The membership value 0.95 to the numbers minus 0.5 and plus 0.5. Similarly, you can assign the membership values to the numbers on either side of the number 0. So what you get is a symmetrical curve as shown in the figure. Symmetrical curve about the origin 0 as shown in the figure with the maximum membership value 1 to the number 0. Now to express this graph, you can see the equation of this graph is say sigma x equal to 1 by 1 plus 10x square. So if you fit a curve or fit an equation to this curve, what you get is the membership function as sigma x equal to 1 by 1 plus 10x square. Now you can see when you put x equal to 0, what you get? Put x equal to 0 here, you will get the membership value as 1. Similarly, when you put x equal to 0.5 or x equal to minus 0.5, because x square is coming in the denominator, either you put 0.5 or you put minus 0.5, that sigma value remains the same, right? So you can get the membership values of these points from the membership function, say sigma x equal to 1 by 1 plus 10x square. Now, how will you identify this particular function 1 by 1 plus 10x square? That is another question. Now, there are various methods of assigning membership values to the given fuzzy set. One of the things is that depending on the situation, you have to draw the graph of the membership function, and then from the graph, you fit a particular curve to that particular graph. Using many methods in statistics or in numerical techniques, we can fit a curve to the given graph. Or there are scientific methods also available to get the membership function of the given fuzzy set. So with this example, now we'll move on to more definitions in fuzzy set. Now I have shown you the next slide of definitions continued. Please tell me when this is visible.
It is visible, ma'am.
Okay, so we are continuing with the definition. So the first one is what is called threshold set. The threshold set is denoted by sigma superscript t, which is set of all x belongs to S such that sigma x is greater than or equal to t for all t belonging to 0, 1. So from the definition, you can see that sigma t is a crisp set. For example, suppose I take my fuzzy subset A as, say, here as say some element, say x with membership value 0.1, then y with membership value 0.2, then z with membership value 0.4. Suppose this is my fuzzy set with x having the membership value 0.1, y having the membership value 0.2, and z having the membership value 0.4. Then I am taking the threshold t, which is any value in the interval 0, 1. Suppose I take t as say 0.21. Then what will be my sigma t, or I denote here by AT. AT now here means all those elements in the universal set S such that its membership value is greater than or equal to T. Now I have taken T as 0.21. So all those elements having the membership value greater than or equal to 0.21 is only one element set having the membership value. So AT becomes the singleton set Z here. And you can see this singleton set is a crisp set or the classical set. It is not a fuzzy set. So the threshold sets are crisp sets. Similarly, if you take T equal to say 0.15, suppose I am taking T equal to 0.15. So what is AT or A.15? All those elements in the set A whose membership value is 0.15 or more. In that case, our set now becomes, or the elements are Y and Z only. So this is again a crisp set. So remember, the threshold sets are crisp sets. Similarly, look at the second definition, support of sigma. Support of sigma denoted by sigma star, set of all x belongs to S such that sigma x greater than 0, or what is known as the underlying crisp set. That is, all those elements in the fuzzy set sigma satisfying the condition that their membership value is non-zero. All those elements now becomes sigma star, and this sigma star is also a crisp set known as the underlying crisp set. So in this example A, what is my A star? A star means all those elements which are having the membership value greater than 0. Accordingly, I will get A star of x, y, z. So, which is a crisp set known as the underlying crisp set of the fuzzy set A. Like that, you can identify what is a threshold set and what is the support of sigma denoted by sigma star. Now, coming to the next definition, subset of a fuzzy set. How will you define the subset concept in the fuzzy setup? That is sigma subset of tau. Here, sigma and tau are any two fuzzy sets. Then sigma is a subset of tau if sigma x less than or equal to tau x for all x belongs to S, where sigma and tau are the fuzzy subsets of the universal set S. That means for sigma to be a subset of a fuzzy set tau, we should have the membership function satisfying sigma x less than or equal to tau x for all x belonging to S. For example, suppose I am taking my A like this. That is the same set I am taking A equal to say x with membership value 0.1, then y with membership value say 0.2 and z with membership value 0.4. Now I am taking another set say B as say x with membership value say 0.2, then y with membership value say 0.3 and z with membership value say 0.5. And suppose like this if I take, then you can see that all the membership values of the elements in A are less than that of the corresponding elements in B. So that means here you can take this A as a subset of B because the values of the elements in A are less than that of the values, the corresponding elements in the set B. So here A is a subset of B. Now A is a proper set. The next definition, sigma is a proper subset of T if sigma x less than or equal to tau x for all x in S and there exists at least one x in S such that sigma x is strictly less than tau x. So that also is true here. Here you can see the value sigma x is 0.1, sigma A of x is 0.1, which is strictly less than 0.2 and 0.2 is the value of x in the set B. So here actually A is a strict subset of a proper subset of B. A is a proper subset of B here. Okay. So likewise you can define the subset concept, proper subset concept, right? Similarly, when will you say, the last bullet here you can see, when will you say sigma equal to tau? Only when sigma x equal to tau x for every x in S like this. So here, whether A and B are equal here, because the value of x in A is 0.1 and the value of x in B is 0.2. It is not same. Here sigma x is not equal to tau x for this element x. But this should be true for sigma x equal to tau x for all x in the set S. Then only we say that the two sets are equal. So not only that, the underlying crisp sets should be same, and also that the membership values of the corresponding elements also should be same. Then only we say that two fuzzy sets are equal. So far we have defined fuzzy set, then example of fuzzy set, then threshold set, support of a set, and also fuzzy subset concepts, and also when we will say two sets are equal. So now we'll move on to the next topic, what is called the union and intersection of fuzzy sets. I have shown you the new slide of union and intersection. Please tell me when this is visible.
Yes, ma'am, it is visible, ma'am.
No, I have shown you the examples first of here, but I have not defined what is union and intersection of fuzzy sets. So let me define first what is union and what is intersection. So I am taking two fuzzy sets, say A and B. So there are membership values associated with A and B here. Then I am going to define A union B as what? Max A union B of any element X. A union B of any element X is nothing but maximum of A of X, comma B of X. Maximum of A of X, comma B of X. Similarly, A intersection B of any element X is nothing but minimum of A of X, comma B of X. Now, let us see these definitions carefully. You already know what is the definition of A union B when A and B are classical sets or crisp sets. That is, an element either belongs to A or belongs to B or belongs to both. So X belongs to A means its truth value P of X is 1. And X belongs to B means its truth value is again 1. But if X does not belong to one of the set, then its truth value will be 0 with respect to that set. In any case, what you have is the truth values if you take for the sets A and B. Suppose X belongs to A with truth value 1, X belongs to B with truth value 1. The second possibility, X belongs to A with truth value 1, but X does not belong to B, then the truth value is 0. Then the next possibility, 0, 1 and 1, 0. So tell me what is the membership value of that particular element X in A union B. The first case is X belongs to both A and B, so X definitely belongs to A union B, so its membership value is 1. Second case, X belongs to A, but it does not belong to B. In that case also, X belongs to A union B, so its membership value is 1. In the third case, X does not belong to A and X belongs to B. In that case also, the membership value of X in A union B is 1. Now the last case you see is both 0. Last case is X does not belong to A and X does not belong to B. So in that case, X is not belonging to A as well as X is not belonging to B. That means their membership value in both A and B is 0. So that particular element will not be in A union B as well. So what I want to tell you is that in this particular situation, what is the membership value in A union B? It is nothing but the maximum of the first row elements 1 and 1. Second also the maximum of 1 and 0. Third also the maximum of 0 and 1, which is 1. Fourth also the maximum of 0 and 0, which is 0. So this concept of max is what is included in the definition of A union B, which is maximum of AX comma BX. So union of two fuzzy sets is defined as the maximum of the membership values of AX and BX. Similarly, you can see the intersection also. For the intersection, you know, the concept of intersection is the particular element belongs to both A and B. The particular element belongs to both A and B. So in the crisp case, if the element belongs to A with membership value 1 and belongs to B with membership value 1, then that element definitely belongs to A intersection B with value 1. But you see in all other cases means 0, 1 or 1, 0 or 0, 0. All these cases, second case, X does not belongs to A and X belongs to B, so it will not belong to A intersection B, so it is 0. Third case also 0, fourth case also 0. So what is happening here is, we are taking actually the minimum of the membership values. In all the four cases, we are taking the minimum of the membership values. And that is why we have the definition A intersection B as, so A intersection B is nothing but what? Minimum of AX comma BX. Minimum of AX and BX. That is the definition of intersection of two fuzzy sets. Now, this example gives you the graphical version of this union and intersection. Now, all of you look at the graph here. The graph here, you know, the graph of sigma. The graph of sigma is this graph. See, like that, I will draw it again. This graph is the blue line I have drawn as sigma. This graph blue is my sigma. Now, my second graph is tau. See, this is tau. Which is that graph? That is this bell-shaped curve. This bell-shaped curve is my graph tau. Okay. So the blue graph is sigma and the red graph is tau. Now, how will you define the union of sigma and tau graphically? Union means we are taking the maximum of the membership values. So maximum of the membership values of sigma and tau, you can see for sigma, to the left of this point here, it is 0. But it is not 0 for this tau. So that means you have to take this curve from here up to here, and then from here to here. Look at the graph I am drawing. The part of the graph like this which lies above is the graph of sigma union tau. Similarly, the part of the graph which lies below means this part. This in green I am showing. The part of the graph in green is what is the intersection, sigma intersection tau. So graphically also you can see the union and intersection of the two graphs. The top portion of the graph will be union and the below portion will be the intersection of two fuzzy sets. So this is how we'll interpret union and intersection of fuzzy sets. So once again, look at the definition. A union B of X is maximum of AX, BX, and A intersection B of X is minimum of AX and BX. So the membership values using the crisp set you can see are the combinations 1, 1, 1, 0, 0, 1 and 0, 0. And accordingly, if you take the maximum of it, you will get the membership value of that particular element in A union B. Similarly, if you take the minimum of the membership values of the element in A and B, what you get, the membership value of that particular element in the intersection. So the same idea only we have generalized to the fuzzy union and fuzzy intersection here. So once again, look at the definition. A union B is maximum of AX comma BX and A intersection B is minimum of AX at BX. So this is the definition of union and intersection of fuzzy sets. Now, coming to fuzzy relation, I think we will come to this after one more point, the concept of fuzzy relation. Let us see what is multi-valued logic. So Anjali, I have shown you the new slide of multi-valued logic. Please tell me when this is visible.
Yes, ma'am. It is
Yes, ma'am.
visible, ma'am.
It is visible.
So let us see what is multi-valued logic, which includes the fuzzy logic also. So multi-valued logic, you know, in the classical logic, you already know there are two values or two proposition only, which is true with membership value 1 and false with membership value 0. Can you see the slide of classical logic?
Still, we can see multi-valued logic, ma'am.
Okay, wait.
Yes, ma'am. Now it comes. Yes, ma'am.
Okay. So in the classical logic, as I have already told you, there are only two alternatives. Either true with membership value 1 and false with membership value 0. There is no other alternative in between 0 and 1. But in multi-valued logic, developed slowly, we have the values in between 0 and 1 also. So let us see in the 20th century. So I have shown you a new slide with a photograph. Please tell me when this is visible.
Yes, not yet come, ma'am.
Okay, wait.
Yes, ma'am. Yes, ma'am.
So you can read
Yes,
it.
ma'am. It has come.
Yeah, so read it. The 20th century brought back the idea of multi-valued logic. The Polish logician and philosopher Jan Lukasiewicz began to create systems of many-valued logic in 1930 using a third value known as possible. That is, in between 0 and 1, we use one more value which denotes the possible, denotes the concept of possible. So let us see how this happens. What is called the three-valued logic. So I have shown you the next slide of three-valued logic. Please tell me when this is visible.
Yes, ma'am. Primitives or some three-valued logics. It's
Yes.
visible, ma'am.
Here what happens if other than 0 and 1, you can see one more value, say 0.5. And there are many three-valued logic. In the first column, Lukasiewicz. Second, Bourgeois. Third, clean three-valued logic. And fourth, hating three-valued logic. And the last column gives you rate-backed three-valued logic. All these logics of three-valued developed during 1930. And they have given the truth values 0, 1 and also 0.5 as given in the table. Now, I am not going to interpret what's the meaning of this, but just to show you, there is one more value they have included between 0 and 1 as 0.5, which denotes the concept of 0.5. That is all that you can just do it now. Okay. Now comes the next slide of quasi-tautology. Please tell me when this is visible.
Yes, ma'am. It is visible, but it is in a corner, ma'am.
Okay, let me see. Now,
Yes, ma'am. Yes, ma'am.
so look at what is quasi-tautology. But before that, I should tell you what is tautology. Tautology means a mathematical concept such that that particular statement will be true irrespective of the truth values of its elements. That is, a statement which is universally true all the time. I repeat, a universal statement which is always true. For example, sun is giving us light. That is always true, right? That particular statement. Such statements are called tautologies. Similarly, contradiction means a statement which is always false. A statement which is always false is called a contradiction. So, in crisp logic or the classical logic, we only have either tautology or contradiction. There is no other concept in between tautology and contradiction. So, starting of the three-valued logic defines the concept of quasi-tautology. Now, read the definition. A logic formula in a three-valued logic which does not assume the value 0 regardless of the truth values assigned to its proposition variables is quasi-tautology. For example, in a tautology, the last column of the truth table will be always 1. But in a quasi-tautology, what they say is that it will not assume the value 0, but it may assume any other value, say 1 or 0.5. Because in three-valued logic, we have only three values, 0, 1 and 0.5. So, any statement which assumes either 1 or 0.5 or which does not assume the value 0 will be called quasi-tautology. Similarly, you can see the definition of quasi-contradiction. A logic formula in a three-valued logic which does not assume the value 1 regardless of the truth values assigned to its proposition variables is quasi-contradiction. Students, please remember the classical contradiction is such that it assumes only the value 0, nothing other than that. But in quasi-contradiction, it can assume the value 0 and also 0.5 but not 1. So if a statement assumes the value either 0 or 0.5, then it is termed as quasi-contradiction. Okay, so that is how in a three-valued logic we have identified the concept of quasi-tautology and quasi-contradiction. Now, this three-valued logic is now generalized to what is called n-valued logic, which I have shown you in the next slide. Please tell me when the next slide is visible.
Yes, ma'am, it is visible, ma'am.
So, the set Tn of truth values of an n-valued logic is defined mathematically like this. That is, you have truth values say from 0, 1, 2, 3, etc. The truth values are say 0, 1, 2, 3, etc. up to n minus 1. Now, we have to normalize these truth values. That is why the truth values are taken as 0 by the total number of values, which is n minus 1. In the second truth value, 1 by n minus 1. The third truth value, 2 by n minus 1, etc. n minus 2 by n minus 1. And the last truth value, n minus 1 by n minus 1, which is 1. That is, we have the truth values from 0 to 1. There are n truth values. The first truth value is 0. The second one, 1 by n minus 1. The third one, 2 by n minus 1, etc. And the last one is the maximum value 1. So, in the previous slide, we have seen the three-valued logic. Three-valued logic means only three values it assumes. Means how will you get the three-valued logic here? N equal to 3. So, what is n minus 1? N equal to 3 means n minus 1 equal to 2. So, which are the values assumed in the three-valued logic? First is 0, which is 0 by 2. Then second is 1 by n minus 1. N minus 1 is 2. That is half. And the third is 2 by n minus 1 and n minus 1 is 2. So you can see the truth values are what? 0, 0.5 and 1 for the three-valued logic. Is that clear? So for the three-valued logic, the truth values are 0, 0.5 and 1. So when n equal to 4, we have n minus 1 equal to 3. So the truth values will be 0. Then next one will be 1 by 3. Then second one 2 by 3. And the last one 3 by 3. There are 4 truth values in this way. Okay. So like that, we can develop the concept of n-valued logic for n greater than or equal to 2 when n is finite. Now I want to tell you, when you take n tends to infinity, what you get as n tends to infinity, what you get, will get infinitely many truth values, and that is what our fuzzy logic is. So infinitely valued logic is our fuzzy logic when n tends to infinity. So like that, you can get the generalization of the logic here. Now I have shown you the next slide of Lukasiewicz three-valued logic, which is the most famous among the three-valued logic. Please tell me when the slide is visible.
Yes, ma'am, it is visible, ma'am.
So this is the most famous one, that is why I am showing you the slide. So the first series of n-valued logic for n greater than or equal to 2 was proposed by Lukasiewicz in the early 1930s as a generalization of his three-valued logic. It uses truth values in Tn and defines the primitives by the following equations. That is, complement is defined as 1 minus a minimum b is minimum of AB, A or B is maximum of AB, then A implies B is definition given by minimum of 1 comma 1 plus B minus A, and A if and only if B takes the truth value 1 minus of modulus of A minus B. So this is the most famous three-valued logic, which takes the values 1, 0 and 0.5 only. Okay, so let us see how this is now generalized to any n. So I have shown you the next slide. Please tell me when the next slide is visible.
Yes, ma'am, visible, ma'am.
So for each n greater than or equal to 2, the n-valued logic of Lukasiewicz is usually denoted in the literature by Ln. Okay, the truth values of Ln are taken from Tn that we have already defined in the previous slide. Tn as 0 by n minus 1, 1 by n minus 1, 2 by n minus 1, etc. n minus 1 by n minus 1. And its primitives are defined by the sequence say L2, L3, etc. L infinity. So L2 becomes the classical logic or the two-valued logic, taking only two values, say 0 by 1 and 1 by 1, which are 0 and 1. So L2 is the classical or the crisp logic, whereas your L infinity becomes the infinitely valued logic, or what we call is now what is called the fuzzy logic. Now we are just discussed, because the truth values are taken from the countable set T infinity of all rational numbers in the interval 0, 1, the infinity valued logic. So here only rational numbers are taken because we have defined our Tn as quotients 0, 1 by n minus 1, 2 by n minus 1, etc. But in fuzzy logic, you know, we take the numbers which are not rational numbers as well. So L infinity, now we can generalize to include the irrational numbers also, and we have now defined the fuzzy set concept as a membership function from the universal set to the closed interval 0, 1. So whatever available during 1930 was this infinite valued logic which takes only rational numbers. But in 1965, Sade has again generalized this infinite valued logic and termed it as the fuzzy logic, which is nowadays known as continuously valued logic. So please understand the difference between infinitely valued logic and continuously valued logic. Infinitely valued logic means it takes only rational numbers in the interval 0, 1, whereas our fuzzy logic is continuously valued logic, which takes both rational as well as irrational numbers in the interval 0, 1. So the fuzzy logic or the continuous valued logic is the most general of all the logics we have defined so far. So the standard Lukasiewicz logic is L1 is infinite valued logic whose truth values are represented by all the real numbers in the interval. So now I denote by L1. L1 now I denote by what? The infinitely valued logic, which take all the real numbers. All the real numbers means including rational as well as irrational numbers in the interval 0, 1. And this particular logic L1 is what is known as isomorphic to fuzzy set theory based on the standard fuzzy operations. So remember, L infinity was denoted for infinitely valued logic which uses only rational numbers. Now on the other hand, here L1, the symbol L1 is used to denote the truth values which takes all the real numbers in the interval 0, 1, and thus this L1 resembles to our fuzzy set theory or continuously valued logic. Okay, so please remember the difference. L infinity takes only rational numbers, whereas L1 takes all the numbers including rational and irrational in the closed interval 0, 1, and thus this Lukasiewicz logic L1 become more or less the same as our fuzzy logic or what is called the continuously valued logic. So that is, with this slide I am going to conclude my talk. So the membership grades A of X for X belongs to X, by which fuzzy set A on the universal set X is defined, can be interpreted as the truth values of the proposition X is a member of a set A in L1. Similarly, that is the truth values for all X in X of any proposition X is P in L1, where P is a vague predicate, can be interpreted as the membership degree of Px, by which the fuzzy set characterized by the property P is defined on X. Students, this is nothing but I shall give you one example. Suppose your statement is there may be a heavy rain tomorrow. There may be a heavy rain tomorrow. That is, my statement P is there may be a heavy rain tomorrow. So depending on today's climate, we can give membership values to the statement P. Now that climate differs from place to place. Now I am here at Calicut, you are there at Thrissur. So I don't know what the climate at Thrissur is. So for this particular statement, there may be rain tomorrow. I will be giving some truth value, say 0.8. But depending on the climatic condition at your place, you may give a value or a truth value greater or less than that of it. That is, the predicate, the vague predicate P, which can be interpreted as a membership degree of Px, by which the fuzzy set characterized by the property. What is the property here? There may be a rain tomorrow here. So we can now give any arbitrary value to the statement P depending on the particular situation, depending on the particular place, depending on any other situations associated with that particular statement. So like that, we can freely associate any truth value to the statement P. But the truth value which we are giving to a particular statement today may not be the same as the truth value which we are assigning tomorrow. It changes from time to time, it changes from place to place, it changes from subject to subject, it changes from person to person. So that much freedom is associated with any fuzzy logic proposition. And that is what we are experiencing in our day-to-day life also. Because today we will be taking some decision, but tomorrow we may change it. The next day also we may change it. It goes on continuously changing like that. That much freedom is given to the fuzzy logic also. So whatever be the changes, we incorporate those changes on that particular day, on that particular situation, and will analyze the data and arrive at the final conclusion. That is how we are getting the logic. And with one more example, I will conclude. See, in our school days, we used to learn that there are 9 planets. And that time we believed that it is a universal truth that there are 9 planets. But now what happens? But now my daughters are saying that no, there are no 9 planets, there are only 8. How that universal truth changed, I don't know. So some of the scientists vote for that 9th planet, and some are against, voted against that 9th planet. And the majority of votes were against the 9th planet. So now that becomes only 8. But who knows whether that Pluto is a planet or not? Nobody knows. But we are assuming today that it is not a planet, but we have assumed previously that it is a planet. So it goes on changing, and who knows, after some years, Pluto again becomes a planet. Who knows it? So that is the property of the nature. It goes on changing day to day. And we have to incorporate these changes to study the concept mathematically. For that particular study, we need fuzzy set theory, which is the theory of uncertainty. So I hope I have given you the glimpses of what is fuzzy set theory is. And with this, I will stop my talk, and the only reference book you can see here, the book by George Clear and Bo Yuan, a very excessive, vast study guide from this book. So I have shown you the reference. Please tell me when this is visible.
Yes, Miss.
ma'am.
So
It is visible.
So book I am referring to you. Make it available in the library also. Those who want to study about the fuzzy sets and the fuzzy logic, you can refer this book by George Clear and Bo Yuan, a very basic book on fuzzy sets and fuzzy logic, theory and application. Application also, you can find a large number of applications in this book. Okay. So with this, I stop my presentation. And I thank all the participants for patiently hearing my talk, though it was very disturbing initially, but I could manage it anyway. So thank you for your invitation to this first webinar series. And also I thank the principal of the Vimala College and all the faculty of the Vimala College and all the other staff, students, and I also take this opportunity to thank all the participants of this webinar series. Thank you all.
Thank you, ma'am. We should thank you for accepting our invitation and coming, ma'am. And after a long time, I could hear once again your beautiful session, and thank you so much, ma'am. Over to Arya Prasad.
Thank you, ma'am. It was a great session. It was so simply presented, and we just understood many of the things that we are just here now only, the fuzzy sets. We have never heard a class before. Now, all the participants are required to fill the feedback form, which is in the sent in the chat box. If there is any doubt, you can ask anyone. I think there is no doubt.
I think we can go to the vote of thanks, Arya.
Yeah. So I welcome Tinu and Vijayan, the research scholar of Department of Mathematics, St. Mary's College, Thrissur, for the vote of thanks.
Okay, ma'am. It was a very wonderful session. Thank you, Dr. Sunitha, ma'am, for sharing such valuable and detailed information on fuzzy and fuzzy sets with us. And I hope we all get a clear idea on why fuzzy is important in our daily life. Thank you, the whole team of Vimala College, for arranging such a webinar series. We are really waiting for the next session to come. Thank you. Thank you all.
Thank you. Thank you once again. Thank you, ma'am. Ma'am, I can't see you, ma'am. I hope you are there. Sunitha, ma'am? Yes. So once again, thank you all for patiently listening, and thank you for cooperating during our day 3 of the webinar series. So I thank all the participants, and thank you all once again. Thank you.